Hello everyone, thank you for attending. We are going to talk about Stirling's formula. Remember the four articles we were talking about, a look at some probability theory, Wallis's formula for pi, Stirling's formula, and the normal distribution. Well, this is the third one in the list, Stirling's formula. Let's take a look at it. Let's try to verify a few things. And let's kind of take it from there. You know, Stirling, and this is, like I said, I'm going to have in all four films, in the film pertaining to a look at probability theory, and in the film pertaining to Wallis formula for pi, and in the film pertaining to Stirling's formula, this one right here, in fact, that we're doing, and in the film pertaining to the normal distribution. So the four films are all going to have all four articles at the end of the film scrolling through. All four articles are going to be the following, as we have already said. A look at some probability theory, Wallis's formula for pi, Stirling's formula, and the normal distribution. All four of those articles are going to be just put together to form one big article, but they're not going to be altered at all. They're just going to be in that order. At the end of every one of these videos that we're doing. So, of these four videos that we're doing. So, same thing's going to happen here with Stirling's formula. Well, Stirling's formula, we can reach some conclusions based on things that we've already done thus far. That's kind of the reason for doing the previous material, so we can always build upon it and do something with it. Stirling's formula is essentially this, right here. Stirling's formula, we will prove to the best of our ability. Stirling's formula is this. Stirling's formula is an approximation of n factorial. N factorial, as n goes to infinity, the bigger that n gets, the better this approximation becomes. With that in mind, as n goes to infinity, the bigger that n gets, the better this approximation becomes. N factorial is equal to the square root of the product, 2 pi, times n to the n plus a half power times e to the negative n. And this, we get very, very close to that answer the bigger the n factorial is. That's pretty fascinating stuff. This is easier to look at, easier to do than this, and this identity, or very close to identity, very much an approximate identity, and essentially for very, very big numbers, for all practical purposes, it is an identity, it is an equation for very, very big numbers. This relationship being able to be viewed like this, and this right here being able to be viewed as this relationship is very useful when you do some of the mathematics that you encounter. It's a very useful identity, very useful formula. This is all heavily drawn from the brilliant work of Courant and John, and from the brilliant work of Sokolnikov and Redheffer. And I have this, like I said, this will be scrolled. This will be scrolling at the end of the video. We talk about this. Stirling's formula gives us an approximation of n factorial in terms of other functions. And that's basically what I said right here. So at least we get very close to it. The bigger the numbers, the closer we get to it. Let's prove this. Well, let's find the area under a curve. And then let's find the exact area under a particular curve. And then let's find the area under that same curve approximated. And we can get it as close as we want to the actual answer. In the limit, if we've got smaller and smaller bars that are being summed together, in that limit, we do get an integral. We do get the integral. So if we take it to the limit, they should be equal. Well, they've got this thing called the trapezoid formula for area and for integral. And basically what you're saying is if something is you know, if they draw anything, I guess you could say, and again, you can see I don't have a whole lot of room for it, guys, but you know, let's have bars that are h wide, small h wide, and you're going to go from f sub 0, the function at a point f sub 0, and then h units away, you'll have a function, a functional value equal to f sub 1. The value of the function at a particular point x sub 0 is, the value of the function at a particular point x sub 0 is f sub 0. At a particular point x sub 0 plus h, which we'll call x sub 0 plus h, we'll call it x1, x sub 1. At x sub 1, and the distance between x0 and x sub 1 is h, at x sub 1, f1 is the value of the function. So on and so forth. Well, they're saying if you go to two adjacent places, add them up and divide by 2, add these up and divide by 2, you're finding a trapezoid that's been turned not the way you're used to. I mean, you're used to seeing a trapezoid, guys, like this. And that's what we're seeing here. I mean, it's the same exact thing, but for our purposes, the trapezoid is being turned something like this. And this would be that'd be f0, that'd be f1, and you're getting the average between the two, and you're getting that height. And this thing is h, so there's the area, and this thing was h. You know, and you're just adding them up like that. Well, there's something interesting that happens. F0 is unique. It occurs one. It's at the beginning of the list. And after n spaces, after n h values, you get f sub n. That's at the very end. This is at the very beginning. They don't repeat. But F1, you know, F0, F1, this one's F1, F2. The other one's F2, F3. The other one's F3, F4. After that, you get F4, F5. You keep getting, you get F1 occurring twice, you get F2 occurring twice, you get F3 occurring twice, etc. The only guys not occurring twice are the F0 and the Fn. They just occur once. Okay. If they just occur once, but the other guys occur twice, what is, for example, what is 2F1? So this is how you write it to find the approximation. F1 and F1 is 2F1. You got the half right here. You got the half h everywhere. Pull the half h out of there, and you got F0 occurring by itself. You got Fn occurring by itself, but everybody else occurs twice. Well, it's 2F1, 2F2, 2F3, 2F4, 2F5. Let's say there's a lot of them. 2F6. There's only one F0, and there's only F, let's say n is 100. There's one F100, and there's one F0, but everybody else, there's 2F1 written down. There's 2F1 plus 2F2 plus 2F3 plus 2F4 plus 2F5. That's great. We'll pull the 2 out of there and multiply it by the half. Half times 2 is just 1. The h stays, and that's where they're getting h here. See, you're pulling out the 1/2 h occurs everywhere here. You'll do the reverse of the distributive principle, which is factorization, and then there's always these 2's occurring. 2F1, 2F2, 2F3, 2F4. Pull that 2 out of there. 2 times a half is 1 times h times all these. Not the F0 though. 1/2 h F0 plus 1/2 h Fn. 1/2 h F0 plus 1/2 h Fn. Added together, that's h over 2 times the sum F0 plus Fn. So that's where you're getting this. And that's J. They call it J, just the approximation of that integral. All right, we'll keep that in mind. And we'll see, we'll get the appropriate function with which to deal. The function we're going to deal with, give you a heads up, the function f is going to be the natural logarithmic function, ln of x. And that's going to be our main ticket for trying to get through this thing. It's going to be Fn of x. I'm sorry, it's going to be the f of x, the function the function f is going to be ln of x. ln of x. All right. Again, we're saying we're shooting for this. Okay, we got a basic blueprint of what we're doing here, guys. We are going to let us look at the area under the curve of the function. Let us look at the area under the curve of the function y equals ln x from x equals 1 to x equals n. N is likely some integer, some positive integer. A very big positive integer probably. So x equals n, x equals 1, and we're looking at finding the area under this curve, ladies and gentlemen. And we're going to look at the approximation by the trapezoid formula that I already discussed right here. So A sub n is going to be the exact area associated. A sub n is going to be the exact area of A sub n is going to be the exact area under the curve y equals ln x, and the approximation, the j we were talking about over here, the capital J, they're calling it T sub n, the trapezoid formula approximation. So A sub n is going to be the exact area under the curve of the function, exact area under the curve of the function y equals ln x. You're going to have to do a good integral here and get the exact area. And then you're also going to get an approximation to that exact area, and you're going to compare the two. Why? Because A sub n is approximately equal to T sub n. And if we take, if we do the partitions very, very, very strictly and keep making things more and more accurate, we should be okay. We should be okay. We should be able to get a real good approximation of what's going on here. All right, so that's where we're going. So let's take a look at it. From there, let's see what we can do, guys. I'll try to be pretty efficient with this one and see how we can kind of go about it, see what we can say about it. And again, you're going to have all the notes at your disposal. If you are in any class that I'm teaching, you're going to have it on Canvas for as long as it stays on Canvas. If you're looking at this in some other medium, it's in the film itself. I have all 4 of those documents, all 4 of those articles scrolling one after the other to make one big article, but they're all there in their entirety. And as we said, it's going to be a look at some probability theory, Wallace's formula for pi, Stirling's formula, which is what we're doing right now, and then the normal distribution. It's all there for you. I'll be honest with you, like I've told people in the past, I've said it in other videos, it seems like the notes are probably the most efficient way to go about it. They're a lot faster than a film. You could probably, you don't have to look at an entire film that might be 4 hours long or 2 or 3, 4 hours long, and you only really having a problem with a half hour of the content that you needed to find. You can look through an article, old school paper right in front of you, and it works as good as anything, if not better. Okay, so here it is. Let's talk. All right. We said they're going to be about equal. Here's the exact area. And I can make the trapezoidal approximation as good as we want to the point where they're going to be equal. I'll tell you what. Okay, that's kind of in the back of our mind in this whole process, I guess you could say. It's the key to the whole process, or at least one of the keys for sure, regarding the whole process on this thing. So let's have a look here. Here we go. Let's get an area here. Let's get the area under the curve. The curve in question, we said, y equals ln x. And I think it's going to be useful for us. I mean, we look at it. The integral from 1 to n is a very big positive integer. Interesting. Remember, we talked about this when we talked about, well, I'm about to say something we already talked about with Wallis's formula. When we did Wallis's formula, we talked about u is a function of x, v is a function of x. The product of two functions of x is whatever it is, right? Well, yeah, true. The product of two functions of x, their first derivative by the product rule, and we've been there. Yeah, we've said that. Multiplied by the differential dx on each side. The differential change in the product function, is equal to u times the differential change in the v function plus v times the differential change in the u function. If you integrate both sides, well, the integral of an entire sum is the sum of the integrals. This thing right here will give you uv evaluated between two limits. It can be a difference between two limits of integration. The other guy the integral of u dv v du. Right, we've been there. We've done this kind of stuff. So how's this going to play out? There's a lot more subtlety to this than potentially can meet the eye, at least initially when you're looking at it. And so hopefully this conversation speaks to that at least a little bit, right? What are we talking about here, guys? Well, I'll tell you what. Why don't you? Who's who? I guess what you'd ask here, guys, you could say the integral of ln x dx and let's see here. Right, we'll say it like that. Well, then we call u ln x. U is ln x, dv is going to be 1 dx. So if dv is 1 dx, if dv is 1 dx, v is the integral of 1 dx, which is just x. So it's going to come out like this. Minus the integral, here's x. That's what we said the v was, right? The v, I reversed the order. It was just awkward to put the x over here. So just the v is the x and the u is the ln x. Take the derivative of this and of ln x, and you got this dx. What's going on here? Well, we started at 1. We don't have any problems with zeros here. We got 1 to n. These are positive numbers. There's not going to be something crazy happening. We've set it up in that manner at least. Okay, so we got that. So what do we got here? ln x dx. We said it's going to be x ln x with the appropriate limits put in place. X times 1 over x is 1. The integral of 1 dx is x. Well, there it is. And I guess I'll do it between the limits that we're going to have to put it in, and that's all it is, guys. It's all that it is. Okay. What do we got? Well, what we got is what we already had. I mean, we basically got x x ln x minus x. And you're going to evaluate that. The entire thing, you're going to evaluate that between the limits of integration of 1 to n. What's that all about? Well, it's kind of interesting. Put the n right here. Yeah, let's go with the top here, guys. Go with the top, right here. Put an n, an n, an n. Okay, sounds good to me. Minus, put a 1 here. Okay. The natural logarithm of 1 is 0. That's gone. This is minus a minus, which is plus, and this is whatever it is. So it's n ln n minus n plus 1. There it is. And that's the exact one that we were talking about, guys, that we're trying to get for this particular circumstance. So at the end of the day, we got it. We got this. I mean, now we need to look at this. We need to play some games with this thing because we're like a far stretch from where we want to go. But at least, you know, if you want to kind of look at something, you're thinking, now, how's this going to relate? How's this going to relate to the factorial of an integer, the factorial of a large positive integer or something like that, right? So that's what this is. Now, okay, exact answer. Let's get a good approximation and take that thing as far as we want. Well, we had set the thing up so we had set it up, guys. You remember? Kind of a weird. Let's just be a little careful here. We had talked about how this thing plays out, and earlier we had talked about if there's n of these items, we said it was going to be, and right. We had said, remember how the formula kind of came out after we did the whole song and dance. How it all came out was there was an H, the gap between them, F1 plus F2 plus dot 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 plus Fn minus 1 plus H over 2. Now we did this earlier. We used a little bit different notation earlier, but this is the exact same mathematics. But this is the exact same mathematics. Okay, great. The function under consideration is you are going to start at, where you want to actually start here. Let me make sure I'm speaking the same language they're speaking here, guys. Right. At least make sure here how I'm talking about this. So we're going to start at 1, and that's this guy. This is going to be basically what you're doing here, guys, is the space between them. The space between them. Well, that's of interest. We're essentially saying here that the way they're going, there's a space of 1 between them. Right, there's a space of 1 between them. So this guy right here is a 1 for the approximation. The F0, the initial one, is you're starting at 1. Here you're going to ln of n. This is 1, this is 2. This is ln2 plus ln3 plus ln4 if you wish. I mean, we're just going to keep adding these, assuming there's a lot of them here. And this is ln of n minus 1. Remember how the gap between the base of the sideways trapezoid, there's that H, there's a span going from 0, there's a span going from 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, from 5 to 6, from 6 to 7, etc., etc. 1 to 2, 2 to 3, 3 to 4, and there you go. The ln of 1 is 0. If you're adding, the 1 here is just a 1. That's a half. What's going on here? When you add logarithms, the addition of logarithms is the same as the logarithm of the product. These all go in a nice order. ascending order. The sum of logarithms is the logarithm of the product. True. Right. So, okay, they kind of did something a little different, but that's okay too. I'm going to write something else here. I got n minus 1 right here. I'm going to just stay it like that. I'm going to say ln of n minus 1 factorial. I'm not done. Definitely not done. There's a better way to write that. What do you say you add, you got this guy right here. Let's try to make this a little easier to look at, or maybe a little more aesthetically viable for us. This is true, period. End of the story, it's true. Tell you what I'm going to do. I'm going to add 0. You're going to think I'm being a fool. I'm going to add 0 to all that. But the way I'm going to write 0 is this. I'm going to write 1/2 ln n ln n plus a negative 1/2 ln n. Well, yeah. Negative 1/2 ln n plus positive 1/2 ln n is 0. Okay, I haven't changed what it is. Yeah, I have not. You're right. Now I'm going to take this 1/2 ln n, this 1/2 ln n, and this other 1/2 ln n, and I'm going to add them together. I'm going to leave that over here. Now I'm going to leave this guy looking like this. What just happened here? What's going on here? I kind of jumped the gun a little bit with this stuff. But okay, so we got all this. You know what's going on. You've got the film. Add these two together. You got Tn equals ln factorial plus a half and a half, 1/2 ln n, 1/2 ln n plus 1/2 ln n plus wait a minute. The sum of two logarithms is the logarithm of the product. The sum of two logarithms is the logarithm of the product. Yes. N, the sum of two logarithms is the logarithm of the product. The product, n, times the quantity n minus 1 factorial is just n factorial. That thing right there becomes n factorial. So at the end of the day, you guys, we got this. All right, we've got a lot. I mean, we've said a lot. Okay, so we're saying this. That's the T sub n approximation. This is the A sub n approximation right here. So there's got to be a game here, guys. There's got to be a game here. Yeah. Here's T sub n. Here's A sub n. Okay. Well, they're roughly equal to each other. Even if we get rid of the 1, even if we get rid of the 1 from the right-hand side, the left-hand side quantity remain comparable. So let's see what we can do here, guys. You're looking at it. Let me keep erasing. I think it's the way to go. They're about equal. They are about equal to each other. Yeah, they are about equal to each other. Are they exactly equal to each other? Probably not. Are they close? Yeah, relatively speaking, they're close. How far off are they from being equal to each other? Probably not a real big number that you'd have to add on to 1 to make it equal the other, or a number by which you would multiply one of them to have it equal the other. And that's their whole argument here. That's how they're doing this whole argument here, guys, to do something like this. So okay, we got all this. You've seen what this stuff looks like. All right, so, we said they're close. T sub n and A sub n, T sub n and A sub n are reasonably close. They're reasonably close to each other. T sub n and A sub n are reasonably close to each other in terms of value. What does that mean? Well, it means what we just said. I mean, right. The T sub n was ln n factorial minus 1/2 ln. I think I wrote it like this, not a big deal. I didn't write that, I didn't write the parentheses earlier, but you understand. Some places we write it, some places we don't. It's not really the big deal there. That's T sub n. To the far left is T sub n. That's this. Minus n plus 1. Even if we get rid of the 1 from the right-hand side, even if we were going to get rid of the 1, you guys, even if we got rid of the 1 from this right-hand side, we got rid of the 1, the left side and right side remain quantities which are at least somewhat comparable in magnitude. Even if I got rid of the 1 right here to quote-unquote make things easier, Again, I got this in parentheses. I don't have this one in parentheses. That's not a big deal. Whether they're in there or not, for consistency in this problem, let's put it like there. But not really a big deal, as long as we know what we're talking about. So, again, we gotta say it again, guys. Even if we got rid of the 1 from the right-hand side of the equation, or approximate equation, if we got rid of this 1, they're on the same order of magnitude. The left side and right side remain quantities which are at least somewhat comparable in magnitude. We're simply looking for the right constant, capital L. Therefore, if we add a constant, capital L, on the right-hand side, then that L takes that capital L is going to take that 1, which was removed, into account, and this L will give us a better approximate equation. The constant L should make the two sides equal or very close to it. The constant capital L is there to make it an equation or very close to it. The constant capital L will compensate for the loss of 1 on the right-hand side because of the two sides, regardless of the 1 being removed, are of the same order of magnitude. We only need the right constant, capital L, you guys. Indeed, such a constant, capital L, could conceivably be 1 that I'm about to get rid of, though this is not the case in this regard. For the record, the original 1 makes it, the original 1 that's here, you guys, just for the record, the original 1 makes it seems a decent approximation, but L is actually a number a little bit smaller than 1. Anyway, this capital L that we're talking about, guys, and you'll see this in the notes at the end of the discussion as well, guys. But anyway, that capital 1 takes into account the fact that 1 was present, then removed. In short, removing the 1 from the right-hand side of the equation and replacing it with a capital L takes all of the original mathematics into account and allows us to get the best approximation to the hypothesized equation. The constant capital L allows for 1 or any other real number to make the two sides an equation. The constant capital L makes for 1 or any other real number to make the two sides an equation, you guys. As we said, conceivably choose from all the real numbers, but only 1 is allowed. Only 1's going to work, you guys. But there is one unique capital L, which is best, and we will find it. And they say a couple. I'll kind of get to that in a second. Okay, let me kind of. I said a lot of stuff, guys. I read a lot of stuff without getting up to the actual equation itself. All right. Let's say it again. I'm saying that T sub n and A sub n are approximately equal to each other. I'm saying that T sub n and A sub n are approximately equal to each other. How close are they? I'm not sure, but they're relatively close. They're on an order of, they're roughly of the same magnitude. There's somewhat of a decent approximation, to say the least. Okay, great. They're approximately equal is what you're saying. Great. Is there, and for a particular n, and let's say we're dealing with n that's big. I think the bigger the n gets, perhaps it's a better equation, perhaps it isn't. We don't know. But let's pick a particular n that's useful for the business that we're trying to do. How far out are we doing to get this to work? Look, guys, let's make a long story short. Both sides are approximately equal to one another. This is T sub n on the left side. This is A sub n on the right side. And I'm telling you, if I somehow either multiply one side or, multiply maybe is not the word right now. For this case right here, this 1 right here, what do you say we get rid of it and add another constant there that'll actually make it work? For all we know, 1 was that right constant. 1 was the right constant, maybe, or very close to it. But I'm going to say to you, yeah, maybe 1 is a very good approximate. 1 would actually make this equal, maybe. It doesn't. For the way we're looking at it, it doesn't look like that's going to happen. But there is some constant that you could put on top of 1, that you could add on to 1, that you could add to the right-hand side to make this an equation. That's their argument. Well, that argument right there, let me just see exactly, I want to let me just speak the same language they're speaking, guys. Because I wrote it in some different ways here. Because it eventually becomes like a multiplication as well. You'll see what I'm talking about. There is a number L. There's a number L that I'm going to replace the 1 with. For all I know, that number capital L may indeed be 1. Or it may be a little bit less than 1. it may be a little bit more than 1. I think we found out it's a little bit less than 1. So this ain't a bad approximation, actually, for a lot of what we're doing, even with the 1 as is. But the L is going to be something, and I want to throw that L in there. I think it's just better. And if it's the right mix, it's very close to this being equal, if not equal. That's the argument. And then they say, okay, that's L. That's the constant you're going to throw on there. They also do this. Let's call big E the base of the natural logarithm E taken to that L. You're going to see why we did this later. You'll see why we did that later. But right now, let's worry about this. Let's keep this guy in the mix. And later on, we're going to see why we got that. So this is, but there is one unique L, you guys, which is best, and we will find it. And big E equals small e to the capital L is another constant, and that is one which we really want. See, we really want this, but I'm not telling you why we really want this yet. You'll see it once we do it. I want to find L. I want to find L, ladies and gentlemen, such that e to the L is equal to something, and that's something I really want. But I got to find the L that could be that L right here to put here. Well, they're essentially saying, guys, if this is a decent approximation, it's an exact answer or very close to an exact answer if you put a 1 there. Replace the 1 or add something to the 1, and that thing you added to the 1 plus something is L. And now they're going to be equal. Okay. Great. I said L. May we exponentiate each side? Why not? It gets rid of a lot of the monkey business that's going on. Let's see if we can do it. So if two things are equal, they remain equal if you do the same thing on each side. I just said these two things are equal. They weren't equal earlier. They were just an approximation earlier. Yeah, I know, but I said if you play your cards right, there is a capital L that could be added instead of a 1. Perhaps it is 1. Nothing changes. But it's some capital L that I could add in place of 1. Let's just put it that way. I could add some capital L in place of 1, and that approximation is no longer an approximation. It's an equation. Or very, very, very close to being an equation. For all practical purposes, an equation. There's got to be an L, a capital L that can do that for me. Well, if they're equal, exponentiate here. Yeah. What we're doing is exponentiate it. Sure. Well, what's so good about doing that? Well, we know that the logarithmic function, the natural logarithmic function, and the exponential function associated with the base of the natural logarithm, e to the x, the function e to the x and the function ln x are inverse functions of one another. If you do one and then the other, you get back to the original element in the domain with which you were working. If I start with x and go e to the x, and then go the logarithm, natural logarithm of e to the x, I get back to x. If I start with x and I go ln of x, and then exponentiate the logarithm, I get back to x. So if you do the logarithmic function and then the exponential function, you get back to x. Take the logarithmic function and then the exponential function, take the logarithmic function, get an answer, and then exponentiate the logarithm, you get back to the original element in the domain. You get back to x. Or take an element in the domain and do the exponential function first, then get the logarithmic function, you're back to x anyway. Do the logarithmic function, then the exponential function, you're back to x. Or do the exponential function and then the logarithmic function, you still get back to x. Well, that's good. If we do all this, we know how this is going to play out. So you do this, you end up getting the way this thing looks right here. Let's get this side. Be careful and do the math that you know how to do. Let's do the math that we know how to do. On the left-hand side, it's going to be e to all this times e to the negative of this. Okay, there's a lot that goes on there. You basically get e to the ln n factorial times e to the negative a half ln n equals see what we're going to say here exactly. Equals, so this right here, you got it, let's kind of time out for a second, guys. This here is minus 1/2 this, which is plus a negative. Same thing, plus a negative like that. Minus 1/2 ln n. Minus 1/2 ln n is plus a negative 1/2 ln n. Does everybody agree? Just do this. I mean, I didn't really do it. In the notes, you didn't see them emphasize this greatly. This times that is the same as the logarithm of a quantity exponentiated is the exponent brought out here times the logarithm of the quantity. I'll reverse that. You got that. What does that mean? Well, that's ln of 1 over n to the half. Wait a minute, to the half is the square root of n. We know that. The other guy, this guy right here. Now let's see what we can let's see exactly what we can do. Let me kind of come over here, guys. We go n ln of n. You can bring that guy and make him as an exponent on top of that, and that's what that's equal to. And that's what that's equal to. So what happens is, guys, you're doing this, you got it to here, you're doing the other guy, Let me put that guy, e to the L, right in front. I'm going to put it right in front of everybody. I'm going to put it right in front of everybody. That's e to the L. This is n ln okay, we've already done this, or talked about it at least. The other one's e to the negative n. What's going on here? Take the natural logarithm of something, then you exponentiate, you get back to where you started. Let's do it again. Take the natural logarithm of something, and then exponentiate the result on top of base e, you get back to the original item whose logarithm you were getting. You get back to here. Do this right here. Now we said negative 1/2 ln n, negative 1/2 ln n, the negative 1/2 goes right here. That's the same as 1 over this to the positive 1/2. You could also write it like this, to the positive 1/2. And that's just the positive 1/2 goes right here. 1 over n to the positive 1/2 is 1 over the square root of n. That's ln 1 over the square root of n. So there it is. What is that? If you take the logarithm and then you exponentiate, all with the appropriate bases here, these are all completely associated with one another. They are inverse functions of one another. Natural logarithm and e to the x are inverse functions of one another. ln of this exponentiated on top of base e is going to give you that's e to the L. That right there, when we were horsing around with that thing right there was to the n. ln of all this exponentiated yeah. True. Let's take a look at, okay, that's it. I mean, period. That looks pretty good. We said that capital E, we defined capital E. I said right here, let's call capital E, e to the capital L. We'll cross every bridge as we need to cross it, guys. Does everybody understand, if you want to solve for n factorial, because we did say that the premise of this was to find an approximation for n factorial. Multiply by the square root of n on each side. Ladies and gentlemen, is the square root of n n to the 1/2? Yeah, it is. So yeah, sure is. Well, that's good. N to the 1/2 times n to the n, you're just adding the exponents. what we have here is n factorial equals e to the L, n to the n times n to the half just make sure we're agreeing here with one another. And I'm agreeing with myself, some of the stuff I looked at, some of the stuff that the great scholars wrote down. Yeah, it's good enough. Okay. Yeah, that looks like something. Pretty important, really, if you're really careful about it. It looks about like what we were trying to find, what we're trying to prove. We're not that far off. Again, we said there was an L that would be added. We'd get rid of the 1 and add an L, which may be the same. That L might be exactly the same as 1. Maybe 1 is the best. Maybe 1 is the best, or it's pretty good at least. Maybe 1 is the best. It's not. It's not. But maybe it could have been, whatever. But we're getting rid of that 1, and we're going to add another constant on there that's not going to let it be an approximation anymore. It's not going to let it be an approximation anymore. It's going to make it an equation. Once I get rid of that 1 and replace it by a capital L, that capital L will fulfill all the gaps. I mean, it'll fill all the gaps in the sense that any difference that was there is basically taken away if I add the right number to it. It was an approximation before, but if I add the right number to it, that approximation becomes an equation. It's not that far off, and if I add the right thing to it, the approximation is no longer an approximation because I added something else to it. I actually made left side and right side into an equation. You got to add the right thing to it to get an equation. Right now it's not an equation. It's almost an equation, approximately an equation. But when I add the right L to it, rather than 1, I'm going to add something else other than 1. Something bigger than 1. Maybe a little bit more than 1. And that thing will be 1 plus that little bit bigger. Something a little bit more. Maybe I got to add more to it. If I add more to it, it's 1 plus a little more. That 1 plus a little more is your capital L. Or maybe I take something away from that 1, and that 1 minus that little bit that I'm taking away, that 1 minus a little bit that I'm taking away is the capital L. But there's got to be a capital L there that takes the approximate equation and makes it into a real equation. Because it's not off by much, and I just want to figure out what that capital L is to make it happen. And that's the process here. We put an L in there, and we claim we did it. Or we claim we got real close. We got a lot closer than we were before. All right, if that's the case, yeah, it's not looking too bad, actually, is it? So we wrote a bunch of stuff here. Let me erase these, and let's see what we can say. All right, guys, I think I ended up erasing a little more than I wanted to, but that's all right. I just write it down again. So I guess this L is kind of a correction factor. It makes both sides equal to each other if I add it on if I add it on one side and it's different, conceivably it's different from what we were initially proposing. If I add this L, which takes into account 1, L is, for all we know, L is 1 plus a small l. The small l could be any real number. It could be positive, could be negative, and that l accounts for it. Here's what you had originally. You tacked on something different, either a negative number or a positive. It could have been 0. Maybe it was the right answer. It's not. It's pretty close, but it's not. So you did any real number here. There's got to be some real number here that's going to make it so that we can get the approximation to be a great approximation. Not just an approximation, a great approximation to the point where it's an equation. That's kind of the way they're arguing it. So basically you look at it in the limit. They write a lot of stuff. So they're always you're looking for like a real good a very, very good approximation, which for all practical purposes can be used as an equation for a lot of what you're trying to do. And that's the whole premise of this thing, guys. So when they were saying n factorial limit n goes to infinity, n factorial e to the L and there it is. Okay, you've seen it. Okay, we're going to let we are going to look, a constant exponentiated, a constant put on top of a constant in an exponential manner is just another constant. E to the L is this capital E. So, let's kind of figure it out. I mean, this is the key, guys, and we're going to get it. We're going to get it. We're going to find what E is. That's the E to the L. It's going to be this guy. What do you say? What do you say? How do we do it? Well, I'll tell you what. Why don't you take this guy right here and solve for E to the L. Divide by n to the n plus a half on each side. Divide by E to the negative n on each side, and you end up getting okay. Yeah, remember that's what happens when you do division like that. Limit n goes to infinity. That becomes this. Limit n goes to infinity. I mean, that's pretty obvious, guys. I'm just the way I'm writing it. Okay. We have the same E above if we replace n by 2n everywhere in the above equation, and n goes to infinity remains in effect. They purposely do something here. And Sokolnikov's brilliant work, you guys. I think it was Sokolnikov, was Karat and John as well that had done this. I think I drew from both. And you're not going to lose. I mean, they've just really knew what they're doing, obviously. Let's have a look. Right, from Courant and John and from Sokolnikov and Redheffer, I drew from this. They're saying, look, this is all true. So, yeah, it's true. You know, does this change at all? As n goes to infinity, as long as it, you know, look, if I make all the n's, into 2n, as long as I consistently change everybody, this thing's just getting to where it's going faster. It doesn't change the destination, it's just going faster. I can get to Chicago riding my bicycle, or I can get there driving a nice sports car. One's going to be faster than the other, likely. You know, so same thing here. If everybody's going at the same in a proportionate manner, yes, this is going to be twice as much. That's going to be twice as much. That's going to be twice as much. That's going to be twice as much. Yeah, the n is equal to n. I get it. And how about the 2n is just equal to capital N? Put a capital N here, 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 and here. And that capital N just happens to be 2n. Yeah, it doesn't change it. It doesn't change it. So they want to do that. I'm not going to put a capital N though. I'm going to leave it. I'm going to put a 2n there, but I'm trying to give you the argument as to what's going on. What happens is, call it, I guess you can call it an equation 1 there. Here goes. Capital N factorial, remember what I just proposed, is 2n factorial. This guy is 2n on the bottom here. Be careful how you write it. You got to make sure it's containing everybody. On top, you got 2n plus a half. The half ain't changing. That was a constant. It stays a constant. This is e to the 2n. True. True. Then they say, it's kind of pretty fascinating. This is interesting. Definitely interesting. Doesn't change what it is. Now, we just said that. Now they're saying, come back to this guy, and this time square all of that. Really? Yeah. Here we go. Square both sides. But don't go 2n on this one. Just call it n. Square this thing. Yeah. Square the other one. Square the other one. That's pretty interesting. That means you're multiplying this thing by 2 all the way across the top. And it's going to be, by 2 all the way across, it's going to be negative 2n. Oh, that's interesting. Negative 2n, multiply by 2 all the way across. You get this. Square this guy. Whoa, a lot of similarities here, and yet enough of a difference that perhaps there's something here of interest. Okay. Yeah. Now what? It's a good question. Now what, right? Man, there's so much going on here. There's a lot of symmetry. There's a lot of everything. Let's talk. Okay. Now what? Take 2 and divide by 1. Take equation 2 and divide it by equation 1. And I'm going to leave that there. Man, there's a lot I'd like to leave, but we know that E is equal to E to the L. So let's see what we got here. And we know that too. What do you want to do here, guys? We got a lot of it here. Let me just erase a good portion of this. We're going to need a little bit of room. What is going on? Well, if you take E squared and divide it by E, you got E. E squared divided by E, you got, big E squared divided by big E. Big E squared divided by big E is E. Okay? Big E squared divided by big E squared divided by big E is E. Great. Well, so what? You've got this divided by that. So, see what we got here, guys. You've got got it. You've got so see exactly how I want to do this. There's a number of ways to play this. My notes go about it in the exact same way, but maybe not in quite what I'm about to try to pull off here, guys. At least right now, you got what I got. You got the quantity, and you got the quantity n factorial squared divided by the quantity 2n factorial. You've got this divided by that. True. This right here, for the E squared, this divided by that. I mean, I think I'm just going to put it on there, guys. I was going to do something. I got a feeling I could probably be more confusing than helpful on this thing, but 2n plus 1 divided by I just saw something that maybe would have made it easier, but the explanation of it, unless you have a live audience, I'm not sure it's a great move. That's interesting. There's a lot that goes on that's interesting, I guess. That's why I cancel the 1. We've got this. We've got it in the notes, so we're not going to worry too much. That right there, stay with it. This guy, because of the negative exponent, you can bring him up here as a positive exponent. This guy, because of the negative exponent, you can bring him down here as a positive exponent. So you've got this stuff so easier done than said. You just don't know who's how we're following this thing when we're doing it. Correct? Not correct. It should have been a half. I'm sorry. And the other one is n on the bottom. Let's make sure I didn't do anything careless here, guys. Yeah, it looks good. It's okay. There are two times n numbers for which you're getting a factorial. Here there's only n. Here you got 2n. Well, that's a good point. Right. When you do this, it's double the numbers. It's a number which is twice as big as there. So there's in a written array. Let's see what we've done here. No, it still stays, but they're just twice as big when you're doing it. So the numbers are just twice as big as they were earlier for which you're getting the factorial. So we really got to look carefully when we're doing this, you guys. Let me talk to you. You can bring this inside and hit the 2. And then hit the n. And this right here correct. Yeah, there's a lot going on here. Let's keep going. I'm not taking, there's an elephant in the room, so to speak, but we're not gonna touch it just yet. Tell you what, let's kind of make it a little easier. This guy right here, 2 to the 2n plus a half is equal to 2 to the 2n plus times 2 to the half. That's equal to, well, you're looking at it. I mean, it's 2 to the 2n times the square root of 2. That's this right here. Okay, yeah, true. What else is going on? Okay, you see all the stuff we're doing, guys. I'm just tempted to erase the other stuff, but I don't think I want to just yet. What about this? n to the 2n plus a half. I remember I broke it up pretty nicely. Plus 1. That's n to the 2n times n to the half. This is n to the 2n times n. You know where this is going, guys. You know, depending on what they're going to use for that. So it's underneath like that. It's, you know, whatever. It's 1 over n to the half. You can say a lot. What do we have? Well, what we have is this. I mean, we're at the end of the day, we got down to here for that top thing, and we got all this other stuff going on, which is of significance, I guess you could say. So let's see what we got here, guys. What have we done? And again, we're just going to spend a little bit of time contemplating some of this stuff. Well, we did a bunch of stuff here. It's on the bottom, the whole thing. Square root of 2. This whole thing, you know, a lot happened. Definitely a lot happened. Right. So we got the 2 is 2 to the 2n times the square root of 2. That gets a little, it can get potentially a little messy here, so let's not do anything careless. 2 to the 2n times the square root of 2 looks good to me, man, from the get-go. Looks pretty good. The other stuff left, got 1 over the square root of, you know, you got 2 over, you got the square root of n on the bottom there on that one. For that, correct. Looks good. For some reason, I'm just not. All right, here we go. We'll write it like that. So, I mean, and they write it. There's a whole bunch of ways they can write this thing. All right, let me leave it like that for at least now, and then we're gonna manipulate it further. I'm gonna try to use some of the brilliant work of the scholars that I'm consulting to do this thing, guys. But we're getting to here. It's like, okay, great. That's yeah, okay, I believe that. But man, that's a crazy number. Notice, depends on the n that you're talking about as well, as far as the e, the e is dependent upon the n. If you take it toward infinity, you should get one answer. And we're looking at this thing, it's the limit. Always, we're talking about the limit as n goes to infinity. So, yeah, I mean, it looks good to me. Look at it very carefully, because now we're going to see if we got a way out here. We're going to see if the stuff that we did earlier on probability theory, but especially the stuff we did with Wallis's formula, Wallis's product for pi, is there a connection here? Is there a connection here? Well, we can look up what Wallace said, and we can look up what this said, and we can kind of figure out where we are. Yeah, looks pretty good. Everything looks pretty good. It looks good, we still don't have an answer, though. I mean, we've got an answer, but it's kind of shrouded in mystery in a sense. Can we take this infinite product, this ratio, and as n goes to infinity? I mean, this stuff is crazy. This stuff is crazy. So, so let's see what we can say, guys. We've done a lot. There it is. Yeah, okay, great. What do you mean? What the heck's going on here? Well, you understand the number 10, for example. This n and this n and this 2n. The number 10 factorial, is a list of 10 numbers from 10 down to 1, going by ones. They're all the integers that are contained between 1 and 10, including 1 and 10, and they're multiplied together. That's 10 factorial. That's n. That n factorial, if n is equal to 10, if n is equal to 10, 10 factorial is a product of 10 numbers from 10 down to 1. All of them are positive integers. You're not skipping anything. They're just 10, 9, 8, etc. Okay? If that's 10. If this is 10, same number 10, 2 times 10 is 20, there's going to be double the numbers. You'll get the 10 factorial, and you'll also get the 10 factorials, you know, you'll go 10, 9, 8, all that, but you also go from 20, 19, 18, all the way down to 11. So you'll get also the 10 that are above that. So, pretty neat. Well, I wrote it, I don't know, there's different ways this thing can get written. I guess the way I wrote it, yeah, it was pretty fortuitous. This is good. This is fine, actually. This is the way we have it in the notes, and everything's looking good. Now we know that E is going to be equal to the limit as n goes to infinity. I'm going to pull the square root of 2 out of here. Pull a square root of 2. You know, there was a square root of 2 there. There it is. In fact, here it is. That ain't going to change. I'll pull the square root of 2. Pull the square root of 2 out of there. You got the quantity. You're going to have actually 2n items. They're just going to be n factorial twice. Here you're going to have 2n items, and it's not n factorial twice, it's n factorial and something more than that. So, but it is 2n items in both cases. This is 2 to the 2n. And this is the square root of n. Wow. Yeah, okay. Yeah, we saw it. In fact, we just for the sake of the curiosity, I guess, guys. Yeah, it's the same thing. Remember when we did Wallace's formula for pi? When we did Wallace's formula for pi. We did Wallace's formula for pi, we found out that the square root of pi was the limit as m, as in mom, m as in mom, goes to infinity. But it doesn't matter what letters I put. What matters is the mathematical reality. definitely a certified mess, you guys, but it's got a lot of beauty to it as well. We said this. Yeah, we said that when we proved Wallis's formula. Wallace's formula for pi was this. Yeah, it doesn't matter what the letters are. You can put alpha in here instead of m. Alpha in here for m, alpha for m, alpha for m, alpha for m. Alpha for m, who cares? You could put an N as in Nancy, in for M as in mom. Put N as in Nancy right here. N, N, N. And here, it's the same thing. Problem solved. Problem solved. That right there is, you know, I don't know which one to use, guys. Yeah. I think we know. I mean, that's the big thing is we know what we're doing. At least we got this guy, and we got that guy, and you multiply by the square root of 2. All this right here that's n. That's square root of 2 times that. Fascinating. It's the square root of 2 it's the square root of 2 times the square root of pi. Guys, the square root of pi. Jackpot. Square root of 2 times the square root of pi. Square root of 2 times the square root of pi is square root of the product 2 pi. E to the capital L is the square root of 2 pi. Yeah, we're not going to worry about that. Let's concern ourselves with this. And that is the same as e to the capital L. What's going on here? Yeah, it is the same as e to the capital L. We just said this guy, we just figured it out, is the square root of 2 pi. So I'll make sure I wrote that right in the beginning, guys, when we're around on the board. Hopefully I didn't ignore to put the square root of 2 pi there. Yeah, it's the square root of 2 pi, you guys. What does that mean? Well, it proves what we were proposing to prove. E to the L, E to the capital L is capital E. And that's the square root of 2 pi. And there it is. You know, it's kind of interesting. Remember, we replaced the 1 by an L. We replaced the 1 by an L, by a capital L. Take the natural logarithm on each side. Take the natural logarithm on each side. Natural logarithm of e to the capital L is capital L. The natural logarithm of the square root of the product, 2 pi, is going to equal something. What was that L? I mean, remember, we replaced the 1 by that L. For the record, that L is about equal to .919. That 1 that was originally there wasn't too bad. It was not bad. It was pretty close. Pretty close. That capital L comes out to 0.919 roughly. And that capital L comes out to approximately 0.919. And E to the approximate, E to 0.919 is roughly the square root of 2 pi. If we knew exactly what L was and could put it there, I mean, at least if we put down a very, very, very good approximation, if we could theoretically put the exact thing on there, this thing would be 2 pi. E to some number roughly equal to 0.919, E to the 0.919 is the same as the square root of the product, 2 pi. That's it. It wasn't, which is indeed close to the 1 that was originally in the estimate. Which is indeed close to the 1 that was originally in the estimate. And there it is. See how I wrote it? I think when I first had this stuff on the board, guys, I had it like this. I mean, it should have been like this. I'm looking. Yeah, I'm looking right at it, so hopefully I didn't miss it. There it is. That's what you're looking at. And there's different ways that it gets written, but that's close. It's close to what we want to be doing. And wow, Wallace's formula came through for us, didn't it? Wow, really, really nice. We had a little bit of a mess going on. Not bad. This is worse things, but that converges to something. This converges to something. Converges to the square root of pi. This right here in yellow converges to the square root of pi, and this is the square root of 2. This converges to the square root of pi in yellow. Square root of pi times the square root of 2, that's going to be square root of 2 times the square root of pi, which is the square root of the product, 2 pi. So this is good. They're equal, or at least close to it. And that's how they kind of write it. I mean, they write it in different ways here. You'll see it in my notes when I do it. But pretty serious business. We see things. There's an infinite product. We were fortunate enough to see it in terms of the sine function. Or other people were fortunate enough to see it in terms of the sine function. They teach us, and we're able to look at it. But Wallace's formula dealt with the sine function and with integrals, and we got to where we needed to go to get the answers that we got. Yeah, that's about it, you guys. They write it in different manners. Toward the end of my thing, I read it like this. The limit as n goes to infinity, n factorial. And there's ways like I said, there's a whole bunch of ways they write it. to me, aesthetically, this is among the best. Uh, 2 pi n to the n plus a half. And there's other ways they do it. They take the n to the 1/2, and that's the square root of n. They put the square root of n, they put n underneath the square root symbol, and they go 2 pi n. But 2 pi, I don't know, I think it aesthetically looks better that way. It's equal to that in the limit. It's equal to it, or it's at least very close to it, guys. So they write it more like an approximation, because it is an approximation at the end of the day, but it's an excellent, excellent, excellent approximation. The more that we got, the bigger that n is, the closer it comes toward, for all practical purposes, being an equation. Very useful to us in that regard. Okay. Well, there it is, guys. So I think it's written like this too, like I said. There's a couple other ways it's written, and I've got it in the notes, so please look at that at the end as it scrolls, as all the notes scroll by us at the very end of the video. There's other ways that this gets written as well, and again, you have access to the entire document in written form. So that is it. Thank you for your time, guys. Appreciate it. Take care. Bye now.